participate. And even if they are making a lot of money,
You're gonna have to see that joke again.
so I actually, the original set, I gave Prescott a choice. 2 cubic gate in 10 years or a 1 cubic gate in 5. They have not even demonstrated a 1 cubic gate. Well, I said you choose, you wanted the extra time. Because if they get a 1 cubic gate, they're probably gonna get a 2 cubic gate within a year. So I was being extremely generous.
Well,
Thanks again. Yeah.
Yeah.
good question.
Yeah, totally. Yeah.
Hey, when you say gravity's not
Marijuana particles. I just think on CDC, people who are older than 60 should expect to stay home for longer.
Like here at MSU, it's so dramatically different.
Avoid these kids, so therefore this should be unpaid leave. No teaching or administrative duties whatsoever.
I mean, I'm not trying to raise you, but I mean,
Oh, it's not.
the planning faculty job is good.
I mean, to my understanding, I have a lot of colleagues applying to faculty jobs and postdocs right now, and the market is just terrible for every person. It seems like, so it is so arbitrary at this point. But you're right, big names do help some degree. So I don't know, what's to say? I still have letters of recommendation from Berkeley.
Okay.
Hope for the best. Yeah.
What sort of, are you applying named fellowships or anything?
I applied to a couple already.
Like Papilaro or?
I did apply for the Populardo. I
Okay,
applied
they
for
already
the draft
decided?
fellowship. They did decide. I didn't. That's just not fun. Also, for a lot of those fellowships, you need to communicate with the professors beforehand,
Right.
and then you need a specific letter of acceptance from them.
We had a couple of them come talk, give talks actually, so.
Oh, okay.
Something like that.
Yeah, I just started applying for those about a month before the deadline because I just am getting in my 5th year. I'm a little younger on the side to actually be searching for jobs. So now, maybe starting soon, I'll send out some emails to try to talk with some of the people in fellowships for those universities.
So is this your first author paper or?
This is my second, due to some, I'll just call it politics. I have 3 more completed manuscripts that are done, and I'm just waiting for a couple people to proofread them for various reasons. So I have 5 publications worth of material in the thesis right now, and now I'm just kind of talking with people to try to push them out.
So do you have a date that,
That's
whenever
not up
you
to
have a
me,
job?
but, I mean,
Who's it up to then?
and it's up to some of the professors who it's more of a political game than a
Right.
science game. But the science is done, the figures are done right now, we're just waiting. But yeah, no, I have a lot of material to put in the thesis, and I have 2 publications right now that are actually out in the world. And I'm hoping within the next couple months we're gonna get those other 3 out very soon. So I'm probably gonna say like within 4 months they should be out.
Okay.
But yeah, no, I'm doing pretty good.
Is Ilya on your committee?
Ilya was my previous advisor before I changed advisors,
Okay.
and this is one of the biggest degrees of politics associated with it.
I talk to him sometimes.
He's a good guy.
Okay. So
But-
yeah, I don't wanna take sides. with
No,
him.
no. He's an excellent guy. The politics is mostly around just how busy it can be.
Yeah.
It's not about attitude or anything like that. One of the biggest things is
But I mean, if you have previous manuscripts you wrote and they held up, I think that'd be like,
It is, yeah. Right now, like for example, Ilya says he wants to do a calculation so he can check one figure, and he doesn't want other people to do it, but also we've been waiting about 6 to 7 months. So
for him to do it.
yeah. And
I mean, I know that he has the kid, but the kid's been around for 2 years now.
no, he has a new kid now.
He's a,
This is.
I've been trying to get a hold of him for 2 years, okay, so it's not just
Yeah.
you. And he told me this morning, like, I'm home with
Oh,
the kids.
no, there's a new kid. Like I think last week the babysitter got sick and etc.
He told me today the
Yeah.
babysitter got sick.
And my other publication, that's not this one, the date on the complete manuscript is 2018.
Right.
And it's finished. And I'm second author, not first author on that one, but
Well, thankfully, my graduate advisor is probably, once I submit
my current strategy is
You are not the only person, you know, who runs around on these things.
not to talk more politics, but this is not specific to graduate students. I know many other professors who have also dealt with legal battles and also so I respect the fact that family takes a lot of time. So I also don't want to take sides too much. But at the end of the day, I just want to either quit the calculation
Right.
or even just like remove the figure that the calculation is related to and submit anything. So I'm sort of just,
Hey.
oh hey.
Oh, I'm not listening in.
Well, we weren't
Cool.
talking shit about you.
I know. Did you like my talk?
I liked your talk.
Yeah.
Did you like his
get
talk?
to your stuff
I liked
until the end.
This is my advisor.
I mean, I knew someone who I guess was a postdoc.
Yeah. So who was that again?
Yang Zhu gave a talk at Chu gave a talk at Tulane maybe a year and a half ago.
I don't know. Yang
You don't know? I knew you. I guess he was at Rice for a while. His advisor was Matthew Foster, and then he went to
Oh,
now you're
that's
gonna-
with Matthew Foster. Okay. Yes. Yes. I vaguely remember.
Okay.
Yeah. I visited Rice several times.
That's right. So when he came to Tulane, he was thinking about living in SUC. Like, logistically, I think he was just kind of something we could do.
I see. When was that visit?
That was the end of 2018.
I see.
I had just had my car repaired, so then I opted to take him here.
Oh, really? I don't.
Well, we never got to reaching out to you.
I see. Okay. Yeah. No,
We actually telecast his talk for Ilya. Ilya had some other, I don't know, I guess he has some Indian woman interested or something that he works with.
Yeah.
Korea?
Korea's, well, that's the only woman, right? No, there's two. There's Angelina and
The new
there's
one, yeah.
one of them.
Well, I don't know which one it was, but
Yeah.
he was sitting there watching we Skyped to his office.
Okay.
You worked on similar work?
I mean, what we're doing is studying transport and kind of, it's not really a nodal line semi-metal. It's like a surface state that splits off from the, like, you know, interesting dispersion part of a nodal line semi-metal, so it's not technically topologically protected.
Okay.
But it's still kind of magically robust for reasons that we don't understand yet.
That's interesting.
So we are using, my advisor studies all sorts of like many body localization and Anderson localizations and stuff, so we're using some of his research and approximations to study transport of the surface states. That's the idea at any rate.
Okay.
Whether
That's
it
really
pans out, whether, I mean, we get
You never know sometimes.
what?
You never know if it pans
Well,
out.
no, we won't, because I mean, so we get, the claim is that we'll get some sort of delocalization and weak disorder, and the argument we're making involves a sort of duality mapping to strong disorder, but a strong disorder you might get some diffusive instead of ballistic transport, and the limiter node is to actually do the experiments and carefully check the scaling, like, so, I mean, this is not, somebody was just sitting there asking me, well, why don't you just do the calculations? I was like,
So who's your advisor again?
Alex Buren,
Okay.
which I mean, I don't know if the name rings a bell to you, but
No.
Ilya does.
Okay. Yeah, Ilya knows everybody. You've met Ilya before.
I've met Ilya several times.
Yeah.
A lot of people know Ilya.
Yeah, he's an outgoing guy.
He's also, I'm louder than I want to be. I was actually just reflecting that I shouldn't have yelled out so many jokes when I came into this room. But Ilya's also pretty loud, so I feel like he like. needs
Ilya is
some
loud and
things.
different. Ilya is loud that reasons, but let me put it this way. I was at March meeting a few years ago.
Yeah.
And I had, you know, there was my advisor was involved in a fight with some rather, well, I guess Altschuler like has some like bone to pick with my advisor,
Okay.
which is, I don't know, I'm sure you know who Boris Altschuler is.
Never heard the name.
But let me put it this way, he's not somebody that you want bone picking with your
Okay.
So they was like, well, maybe you don't want your name on this comment, like, you know, and you know, maybe people are holding it up, but maybe you want to be second author or whatever. And I was like, okay, fine, I'm not fighting about authorship, but then it gets out, and then. You know, I'm at March meeting and Ilya's like, yeah, so what the hell are you doing? Like, why haven't you published anything yet? And I was like, well, look, there's this comment, and he says, Altschuler's like gunning for me or whatever. Well, at first I was like, oh, real soon now. Ilya, I don't know if you've ever been a victim of like the Ilya, like shit-eating grin, like, I don't believe you.
That's a common Ilya grin.
Yes.
It-
No, I like Ilya and I don't want to punch him in the face, but if it wasn't anybody else's face, I would punch him in the face. So he just like, and I explained the whole thing. I was like, well, he said that Altschuler is blah, 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 so like, you know, I take second authorship, but I'm not going to like, you know, work further on this.
That was a
Ilya
very
like,
nice presentation, actually.
So like,
I
Yeah.
managed to go through.
I
also
believe you
the
grin once you realize that, like,
Majorana Fermi also,
I like
which
I can just watch like a
started-
movie.
Yeah.
Yeah,
bit tired,
he's
but
heavy.
I managed
He's
to
a really
follow
good
everything
guy to
until
talk
then,
to.
which
It
is
is.
nice.
It's the
Really good, actually.
so many
Yeah,
things
I
in his
appreciate
life, and
it.
he's
I
also
appreciate
like
it.
the
Trying to make it
it
accessible.
got
I
canceled,
really found
and
it
then he was
accessible.
thinking about moving to party for
That
senior
was
graduate
helpful.
students and
Really,
things.
that's canceled the virus.
Yeah,
It's
right.
fine.
There's just like there's
Um,
so many things
You should
as
be
part
able
of
to
that.
submit
It's
the
just so
paper sometime
stressful to
soon, but
get
we're still waiting on the
things
collaborators.
out, and I
That's
guess
the
I don't
issue.
know how to describe that.
So,
Because
yeah.
that's
Yeah.
politics.
That's what it's
How
funny
many
that it's
years are you
great.
in?
Let's see
This
if
is,
we break any
well,
news.
I'm about to finish my third year.
Only third.
Yes.
I usually
Yeah.
teach them.
I came in 2007, so I'm about to finish my third.
I see.
Yeah, I know that's
You got time.
definitely a little
Oh, yeah.
strange. Yeah.
I mean, I have 3 years on average.
Are you talking about Majorana's over there?
Yes.
Are you a fan of the Majorana's?
I became a fan. Apparently the theory is very, very interesting.
I like the intersection between working with materials and that's just making steps forward in the quantum information side. I know things are really far away, but that's actually the point why I really like working into it, because I like inching closer as we can. So yeah,
Are
it's
you doing
really
stuff on thermodynamics and stuff like that?
I was trying to do it on my own,
So
but
are you gonna go to March meeting and give this?
I got into a research project. John told me to work on some project, so I started doing that and the thermodynamic stuff.
I think on this topic.
I'm not
gonna.
I am working on it whenever I have
that was my
time.
figure.
And that's happening in collaboration with my advisor. So,
Gotta go talk to
it's taking me a long time.
What's your name, by the way?
Noah? Yeah.
Noah. I'd give you a handshake, but I
No,
won't.
it's smart to do
Nice to meet you.
something with Dowling. That's very smart. It's who gets something, get it out.
Right.
Dowling
That's what you want.
really helps a lot of his graduate students. It seems like a lot of them end up in really great places.
Yeah.
Yeah.
The thing is, they're U.S. citizens. I'm not a U.S. citizen, so it might be more difficult, but
Do you-
I still have the hope.
Do you want to?
Very good.
Do you want to be a U.S. citizen? You don't have to.
Yeah, of course.
Okay, okay. That's good.
It takes a long process though.
It is, yeah. Mahmoud's still working at it, but he got his green card.
So the green card is basically a permanent thing?
Yeah, I believe so.
It'll never be.
Right. He will be able to apply to a citizenship after he gets the green card after like 5 or so years
Yeah.
from getting the green card. So yeah, green card will let him get in and out of the state without having any issues with passports and
Right.
visas and stuff like
Still,
that.
I would expect Dowling is so well known that you should probably have. It shouldn't impact too much that you're not an American student. Do you think that's a big deal?
Well, when applying for a job, it might be.
Some jobs you just can't have them.
That's true.
You're
And
gonna
I
work
think
at the
even
DoD or something.
Mark mentioned that he had like some classified jobs in national labs.
Well, that's exactly
Yeah.
the ones that I.
For information theory, that may be
Right.
a bit of a bigger
Right,
scope.
exactly.
Okay. Cool.
So that.
What did you like about this talk? What's your favorite Majarana?
No, okay. I like the theory, that's for sure. I can
Yeah.
tell you that. That was my most favorite part, and that's
Yeah.
usual because I'm a theorist as well,
Yeah.
right? So,
And
and
I
I think it was clear enough so that I could really understand what's
Yeah, you
happening.
did a really good job. Now your comments on my presentations make sense as I see your presentation and
Oh, yeah.
break things down. And in fact, I have a habit of having like one slide at a time and I don't stagger what
Yeah.
comes out, but that
Right.
seems to be a really helpful thing, actually.
I find it also helps when I'm sort of reviewing the slides, as because I basically make the animation at the end.
Oh,
By animation,
okay.
I just mean like one of the things
Yeah,
before
that's
the things
true.
come out.
Yeah.
I never use anything fancy, but I mean it helps me think about what I'm going to say next.
Yeah, because I definitely like throw 6 figures at a time all at once and it's hard to digest sometimes. Cool.
I think the slides were not too, they were easy to interpret. So that was also nice.
I just wanted you to say the sentence, you can send in one electron that gets split into 2 Majaranas.
I didn't get to that.
Yeah, you
Yeah,
didn't
that's
say
the
that
thing.
directly, yeah.
I know.
But you
I
can
know.
just like flick one electron in and then it breaks apart and how that, because they're talking about current and how current
Yeah.
can be used in code.
Yep.
But you're just sending in electrons along the line and they split in a cool way.
Theoretically.
Theoretically. That's
If
the
you
thing.
believe theory, which we do.
Oh, sometimes, but yeah. So, exciting. But that's an interesting question on coherence time and things and the time involved in sending current as opposed to the more mechanical process of moving a vortex one by one. So, it's pretty cool.
Well, I think the decoherence time would change because these gets
That's a great
It's,
question.
it's probably related, the decoherence time is related to the gap in the spectrum.
Yeah.
And the gap is small. Because
Yeah.
it's efficient states. So,
So when should we do it? Before mine?
Oh, is there a quick
Yeah, I would say right as quick as possible.
Alright, so that's fine if that, like, they wait a
Good
couple
talk.
minutes until I
Thanks,
tackle
David.
it from my door.
Try to do it as fast as possible. You can try to do it while the.
Yeah, you know David, right?
Okay, okay, no problem. You're just talking at the door, you should probably tell them that.
Okay, so we've got our last three talks of the day, and we're going to kick it off with Honor Donacci, classical and quantum treatment of self-healing for actual beings interacting with nonlinear optical systems for multi-stage with quantum information processing. New winner for
Yes.
the longest title. So,
I mean, I changed my title even with that. I'm the winner.
so Honor's here from Tulane, works in Ryan's group. So
Which presentation?
we'll hear about that.
On the machine?
Yes, on the machine.
Just hang on until I get back to my seat so I can turn the audio back on after I say change it over. You quote 2020.
Yes, am I? As well.
Yeah.
Thank you for the kind introduction. My name is Honor, and I'm the winner of this competition. Like, who gets to have like title which is the longest. And even when I changed mine, I slightly shortened it. It's still the longest. And I'm a member of like Glasser group in Tulane. I wrote Glasser in Comic Sans because, like, as you might going to see, this is going to be the ugliest presentation because I had to do it like very slow, like quick and dirty, and I put function before the form, and there are lots of handwriting. So first, I'll be talking about mode decomposition, and I'll be going through some physical and computational technicalities because it took maybe a year of mine just to figure this out. So I think the new researchers could benefit from it. And second, I'll be talking about basic classical diffraction theory of like apertures of like for paraxial beams, but in terms of like this mode decomposition theory, such that like I'll be talking about some matrices which represent like the interaction with like spatial mass or turbulence, and then I'll be talking about some special type of paraxial modes called self-healing modes. And third, I'll be talking about what we are doing in the lab basically, and then which is being like seeded four-way mixing. So it will be phase insensitive amplification, parametric amplification, but I'll be talking about how it's going to be effective if we use structured pump. And so first I'll be talking about like semi-classical treatment, and then go over the full quantum treatment. So paraxial approximation on first, for light propagation or any electromagnetic field, we have Maxwell equations, and you constrain it. You have like you have a light beam which is heavily polarized in one regime. It becomes scalar Maxwell equation, and then you further make approximation, becomes Helmholtz equation, and later if your beam is constrained to a beam like a ray or something like that, so it's not divergent far away from Z, then you end up with paraxial beam equation, which is just a diffusive equation, like, or it's also called optical Schrödinger equation. And it has these eigenmodes in Cartesian coordinates is like Hermite Gauss modes, which look like this. For 0, 0, you have like a fundamental Gaussian mode, and then you have all this higher order modes. And for if you solve this in cylindrical coordinates, then you have this Lagarde-Gauss set. But this, yeah, and they look like this. So as you increase the P index, you get like, it looks more and more like a bullseye pattern. And if you increase like the L, you introduce some topological singularity, or OAM, and then like, so at the end you get this dot in the center, which becomes a vortex. And the reason why we are talking about this is basically physical, so because I'll be mostly talking about like the multi-spatial mode, but like usually like when we talk about what is the fundamental basis, fundamental block of this, of like single mode of light, we usually think it as these pixels, and even for like image processing, even when you're not talking about this paraxial propagation, you could decompose like anything, for example, in terms of this pixels, right? This smiley face composed of many of these pixels. But if you were to propagate this pixel, then like this this supposed fundamental block actually diverges, so it's not shape invariant. So it might not be the fundamental basis of this problem. Likewise, you could use these angles to decompose this, which is actually your Fourier analysis, and your just thin lens, ABCD thin lens, basically decompose your beam, for example, into all these angles. But still, like this wavelets of like Fourier transform, like all these angles, also they they diverge when they are propagated, and like, they don't preserve their shape. But these fundamental eigenmodes such as Lagarde-Gauss, Hermite-Gauss, when they are propagating, like they get larger and larger, or like when they go through like this ABCD elements such as thin lens, they just change their shape. Sorry, they just become larger, but like they maintain their shape. And then like you can decompose this smiley face, since these LG beams being orthonormal set. Basically, you can decompose them, and then like, once you add them back up, you get your smiley face back. But there needs to be some concerns, like because there are just two parameters you need to choose when you are decomposing anything in Lagarde-Gauss, which is being this beam waist parameter. So it means like in this waist plane, how large it's going to be, and also like the focal position of this. And then like, if you choose this, then you can decompose anything like in any 2D data which is used in image processing too. But in our case, any electric field in that. And one technical issue is that like how we are going to choose this is actually like in this paper, like people show like without using any a priori scale information, just from looking at the propagation of the intensity pattern alone, you get this m square beam quality factor. And just by using this beam quality factor and then like your usual beam waist from your intensity pattern, you could choose this fundamental LG basis beam waist for given beam, and solve it. Also, another technicality is that like when you are trying to compute this, usually you can't use infinite sum of modes, and usually like only a finite couple of them affects this decomposition. So you truncate to like some maximum L max, some maximum P max, and for this presentation, and I just use an ordering and I use a single index S, such that like you are bounded by some S max on finite amount of modes. And another concern is that like if you are once you are trying to simulate this, you need to sample this on some numerical mesh grid, And even though these LG functions are extending infinitely, you can just limit to a spatial extent, like for Cartesian maybe x max and negative x max, and for polar grid maybe up to some R max. And also, just like the discrete Fourier transform, as you are sampling this, you need to be careful about the LG HG equivalent of Nyquist sampling theorem. So for example, if you are trying to take Fourier transform, if you haven't sampled enough, you won't get accurate results. That's why you need to be using a ton of grid space. A ton of grid points when you are discretizing this LG HG discretization problem. And having done this, you could use your favorite data integration method on a given mesh grid, such as Simpson's one-third rule, trapezoid rule. This is one kind of method. Or you could just use least square regression, such that this is especially good for if you are doing for intensity patterns. And at the end, your whole beam or your whole picture is just represented by a vector of coefficients for given parameters. For example, this is my cat. I just decomposed it into some indices and then added them back, and then voila, just get the same result. And for classical diffraction theory, this mode decomposition theory has been in use since 1970s. Is that let's say for a given plane throughout the propagation axis, let's say you take the slice, and then at that slice, if you decompose your beam into this coefficients, then you can basically find your E field far away. And you might be obstructing or imposing some aperture, or using, or your beam might be interacting with turbulence, such that any spatial mask, a beam which is being affected by any spatial mask could also be decomposed, and such that this between input and output LG coefficients, you can find this. You can define this tensorial elements. And for finite set of modes, and then also finite extent on spatial mesh grid, these just turn to become this matrices. So basically, you have your input beam modes, and then your obstruction, your turbulence, your whatever, basically just linearly transforms it into this output modes. At the same time, this basically transforms this input coefficients into output coefficients. But some other ABCD elements, such as your length, is basically acting on this input parameters, such as the beam waist and then focal position, and then without changing these coefficients, they are changing it. I told you it's going to look ugly. My hand drawing is very bad. Let's say you have some input beam, and its coefficients is passed through some spatial mass. You get output coefficients, and any ABCD matrix just changes its coefficients. Yeah. And as a result of this mode decomposition, you can write any aperture or any field interacting with spatial mass is a combination of these two fields, which is the first one is basically interacting with this diagonal elements of this transformation, which is basically each mode being attenuated, and also the rest basically scatters these input modes into various other output modes. That's why you can write them as such. And having said that, I'm particularly interested in like the self-healing type paraxial beams, such as Bessel-Gauss beams. Bessel-Gauss beams are one kind. They are limited diffraction beams. That's why, like, as they are propagating for a distance, like they stay more or less collimated, and up to some distance. And also, like, if you obstruct, let's say, some part, either centrally or like non-centrally, in some field, in some region, you will see that it's going to be healing itself. And you can generate this BG type of MOS, for example, by using this axicons, which are just conical lenses, or like using this infinitely thin apertures. And so what I found is that, maybe I go a couple slides further first, is that like for modes which are higher order in P, which look more or less like a bullseye pattern, once they hit by an obstruction, they see the same amount of attenuation. That's why this beam interacting with some obstruction can be written down as like the input beam, which is being attenuated by a factor, plus a complement, an error term. And since these complement error terms are like
You mean
these,
a complement?
the complement, yeah, not the, yeah.
This is, you look very nice today, Orna.
Yeah,
That's
yeah.
a very nice compliment. There's an E in that one.
Yeah,
Okay.
this was a
Don't
nice.
publish it with the I.
Yeah. Thanks for the compliment.
That's a nice compliment.
Yeah. And so, as a result, I mean, like this complement term, since it's being composed of like this higher order terms which scattered away, and then these higher order terms are diverging with a rate of beam propagation factor. So with a factor of beam propagation factor, like they diverge faster. And that's why, maybe I could write it like this. So let's say before going to Bessel-Gauss beam, just for looking for like the high P order LG mode, like LG 020 mode. Even for that, you see that like once you implement an obstruction, it just splits into this attenuated original beam times the plus the complement. And as it propagates, even though this stays relatively the same, even though it just gets spatially larger by a tiny amount, the complement diffracts away super fast. Yeah, the complementary.
Find and replace.
Yeah, okay. I mean, over here, in this portion, like this small portion, like it was carrying like 50–60% of energy, but as it propagates, just suddenly, bam, like just now inside this, there's only like 3 to 5% of energy. But for this, it stays relatively the same. That's why, as a result, if you are only looking for this inner portion of the beam in this subdomain, you will see it's healing itself because you basically offload this chunk, you externalize your complement beam.
So now the color scales are to indicate intensity, right?
Yeah, because these
Bright
are,
is
yeah.
high intensity, so those scales can't possibly be the same on all four, are they?
No, I should have been careful about it, yeah.
Yeah, so the light, the blue there
Mhm.
might be an order of magnitude dimmer on the other
Yeah.
scale.
Yeah. I didn't put a color bar to it.
Okay.
But yeah, I mean, long story short, like this is just basically like this energy is externalized for this complement. But
So what I'm getting at, when you
yeah.
do the self-healing, it's pulling in energy from these outer wings and doing
Mhm.
the self-healing, but the energy is not infinite, as
Yeah.
you know, and so it gets dimmer. So you
Exactly.
reproduce it,
Mhm.
but at some point you're not going to be able to see it.
Yeah, it's attenuating by this factor of like beta, which is just this B matrix diagonal element.
Okay. But if I was to plot this on the same scale as that, you wouldn't be able to see it, I bet.
Yeah, true.
Okay,
Yeah, fair.
that's not a compliment.
Yeah, and as I told you, like for example, like some other type of self-healing beams, such as Bessel gauss or like circular air beams, are composed of just real element sum of like all this, all this higher order modes. For example, for Bessel gauss, it's from 20 till 50, and then like for over there, like the attenuation experienced by each mode is more or less the same. It was like 92% or something like that. That's why, and you can see it from here, like for example, this red one is your input Lagarde-Gauss indices, or not indices, or coefficients. And they each get attenuated by 92%. At the same time, like some of the some other modes of the complement is just scattered away. And that's why at the end, for the intensity pattern, like you see like inside some self-healing subdomain, for example, if you look only within a disk near the propagation axis, you see that like this in the intensity pattern, like this terms looking like terms involving E just going to 0. And that's why if you use any similarity metric between unobstructed original beam and the obstructed and yet reconstructed beam, you find that you can use, like we used in our previous work, correlation coefficients, or like some other people use Lebesgue integral cosine. We find that like at the end, like it healed itself, and then they look more or less the same. For example, this is the case for Bessel gauss. So your original Bessel gauss beam, you obstruct it, now it has this hole in it, and then like it is now, you can think this as like being separated out into attenuated original and the complement, and then again the original part didn't diffract, yet this complement just diffract super fast. Another reason why this diffract is super fast, because like smaller the beam you have, it will faster the diffraction you will see by quadratically, because Fresnel number is a power of W squared. For example, this is from our previous work. In our previous work, we generated by using some nonlinear process some sort of bullseye pattern looking like beam, and in that one too, if you are only focusing for the inner part of the field, it will, the unobstructed beam will be going up to some point, to Z max, and over there it will start getting decollimated, and at the exact same spot, your obstructed yet reconstructing beam is fully reconstructed itself. And in our work, we find that distance is exactly the Rayleigh range of the underlying LG beams. Yeah, so they exactly heal themselves at the underlying Rayleigh range. And so is the case for the this combination beams, such as like Bessel gauss, circular, airy, whatever. And having said that, let's say I were to use this self-healing. Yeah, it's this is the work from folks in LSU, in particular Nick Lenning, that he graduated. And so I used this formalism of semi-classical formalism first to compute the how the generated conjugate and amplified probe beam would look like. And in this case, I'm talking about the four-way mixing process. In this process, like this is a double lambda process. We annihilate two pan photons, these green arrows, And as a result, like we generate a probe photon and a conjugate photon. So it's under the parametric approximation, it's Hamiltonian looks something like that. But the nonlinear polarization of this two photon resonance process looks something like this. Again, like you, for let's say you are generating a conjugate photon, and to do this you annihilate two pump photons, and you are at the same time generate probe photon. And this is, by the way, under first-born approximation of non-homogeneous paraxial Maxwell-Schrödinger equation. And to do so, the computation looks something like this. Let's say this is this chi3 being your, and then this is the z-axis. Let's say this is your nonlinear medium, and then like your pump square beam profile, 3D beam profile, as well as your probe beam profile, like probe star beam profile, overlap within this medium, and then you quantify this overlap by calculating this mode decomposition at each slice, each of these planes, and then like integrate over them. So, and at the end, like it gives you how much these beams overlap inside this nonlinear medium. And this new LG parameters tells you how your generated conjugate and or generated probe beam looks like. So for example, this is one of the preliminary results. Let's say I have like this BG beam. I obstruct this to the side of, to the right of your propagation axis, and at the end, like as it travels, like it healed itself, even though it loaded its, it offloaded its problems to the side, and let's say this is your obstructed beam LG indices, and like because of this non-axial obstruction, like basically you have like now all this you have now this OAM contributions as well. But once you focus into the center in the domain, you end up with this bullseye pattern. And another paper that might look familiar to you. This is also from LSU folks. Now, I also used this quantum theory for these nonlinear systems as well, for these multi-spatial mode nonlinear systems. In the case of spatial structured pump, I calculated squeezing parameters through this integral. Basically, in that case, again, like you have your pump spatial profile, the 3D, just like I showed you before, and then your you use like Gaussian probe, and your vacuum conjugate also come out as Gaussian, because we, in a sense, like by seeding this nonlinear process, we structure the density of states of the modes that are interacting. Even though, like in the vacuum seeded case, you would be having like all these contributions of all these plane wave contributions of the modes. But since the seeding vacuum conjugate will be mimicking our probe seed, I think we are justified to use this. So for the unobstructed and reconstructing self-healing beam structured pump and Gaussian probe and conjugate, Gaussian probe and conjugate seed, I calculate squeezing matrix elements, and but with only one difference, with only one caveat from the paper is that like our process is a seeded, like it's parametric phase insensitive amplification process. That's why I'm taking this input beams Lagarde-Gauss mode indices as coherent state amplitudes. In that case, I mean, for example, I'm trying to find how much any of the quadratures are squeezed, then you are basically calculating for like some sort of you are making a calculation involving like this operator algebra, and then your probe, your conjugate is vacuum, but your probe is now displaced to being a coherent state. As a result, you have like parametric phase intensity amplification. But it doesn't change it. Yes.
I mean, S3 is an element of some algebra, or?
Yeah, this S chi, SC is, sorry, I might need to take a step back, is, you have, let's say, this interaction Hamiltonian,
Okay.
right? And then like, it is like quadratic in this creation and annihilation operators. And the power term in front of them, like the factor in front of this, is this chi1. And if you integrate it, you get the 3D version of this chi. Like, so basically overlap of all the modes.
The chi there, it's not even a vector, it's a tensor, I think.
I mean, yeah, it's
Yeah.
usually it's tensor, but for this case, it's only just 1D, because I'm only looking for structured pump, while everything is just fundamental mode. And so this is basically the power of this interaction between this chi3 nonlinear interaction, and if you integrate this to get unitary time evolution, this chi basically is like, this xi is basically gives you this unitary evolution.
Some propagator or something like that.
Yeah, this is a unitary evolution, unitary time evolution operator. And then like, that's why like now this is in Heisenberg or like Dirac picture.
Yeah.
It's a multi-dimensional squeezing operator.
Yeah, that's it. Exactly. And yeah, and squeezing, if you're not familiar, is that, let's say you have I mean, easiest example, let's say you have momentum on position. The more you know about the momentum, the less you know about the position. Like, it's over there, like you are squeezing the noise. And like for the light, it's for example, the more you know about the amplitude, the less you know about the phase or whatever. Another ugly looking figure.
So maybe like 1 or 2 more minutes. We're
Yeah.
running out of time.
Sure. As I told you, like, so my both our previous experiments and like my simulation like models this system in a sense that like we have this our nonlinear medium, which is like this hot atomic vapor, and over here we are driving this process with this self-healing beam, either unobstructed or obstructed and being reconstructed, and also you are using this vacuum seed is the fundamental 0, mode, and you have like your vacuum conjugate, and they are interacting with the cell. And then like this, I assume this cell is from z equals 0 till the Rayleigh range of the fundamental LG mode of the self-healing mode. And what else? And as a result, so you generate this amplified probe, or like you create this generated conjugate beams, and this overlap leads to this squeezing, right? And like I'm obstructing the beam right before the entrance of the cell, right before the chi3 nonlinear process starts happening. So for the case like when I use 0.1, when I use both small probe and pump beams, then I don't see that much of squeezing. So for unobstructed beam, I see like 0.83 dB of squeezing and like 0.91 dB of squeezing, and the beams look like this. The generated beams look like this. Even though they show some signs of like this bullseye pattern, they are lacking most of it, and then like this is how their LG coefficients look like. a similar one for like smaller pump and slightly larger probe, as well as like a smaller pump and a very large probe. But once you have intermediate size pump and the small probe, I find that a really Bessel Gauss looking kind of generated mode, and as well as like the self-healing mode. And as well as the generated mode also shows self-healing, and I saw up to 5 and 4 dB of squeezing for both unobstructed and obstructed beams.
All right, I think
Theory, this is all theory.
Yes, all theory. Yeah.
so we need to wrap it up here. So
Yeah.
I mean,
Yeah. This by the way, this is
Okay.
just this,
okay.
and then it gets smaller when once they are the same size. Gets smaller and smaller, and like once it's to the 3 and 1, we lose it again. But like for the sweet spot, we get like up to 5 and 4 dB squeezing. Yeah. And so to sum up, we use LG or HG modes as like the fundamental building blocks of like this multi-spatial modes, because pixels are not physical. This is the fundamental building block for this. And also like we feel like high P order, like this bullseye pattern looking modes or combination of thereof, then they can be factored out. The obstructed ones can be factored out such that like we know the complement will diffract faster and our beam's going to heal itself exactly at the Rayleigh range. And if we use this to pump a nonlinear process such as four-way mixing, we see that like smaller probe beam will be exactly focusing at the center and leading to squeezing of both unobstructed and obstructed beams. And for the future work, I'm looking for spatial structured probe beam as well, and then like different obstructions such as turbulence, and different self-healing beams, and I'll be doing some optimization and also looking for multiple pump scales. So thank you so much.
All right, let's thank Honor again, and since we're running a little behind, we'll just if you have any questions, maybe ask them after the session. And so we're gonna have a dinner afterwards. Did you want to get like a rough count here?
Yeah, who thinks they're gonna come to the dinner? Raise your hand,
Is
please.
it immediately afterwards?
Yeah.
So where is the dinner and what time is it? That might affect people's count.
We'll just go over to Chimes.
What time, 6?
We'll just head there after.
We'll just head there after the
Okay.
dinner. Yeah, let's say like 5:30.
5:30.
Okay, so how many?
Alright, did you want the
It's
presenter?
close. It's like a 15-minute walk from here.
All right, yeah, this should be very simple. We don't need a reservation.
I know, we just walk in and we wait at the bar until the table.
Yeah.
All right. So are we getting kicked out at 5 promptly, or? Okay.
Not necessarily.
Okay, we should keep it moving though. But so our next speaker is Dr. Vineet Kaur. So she just had her defense yesterday and did quite well on that. So we're all very pleased about that. And she's going to be talking about multipartite entanglement and secret key distribution in quantum networks. Vineet is here at LSU, working with Mark. Going to be at Waterloo next year, I believe.
Yes.
So. Moving on in the world. All right, thank you.
Thank you. Okay, so I'm going to talk about multipartite entanglement and secret key distribution in quantum networks. This was a work that I did in Japan, in Tokyo last year with Masahiro Takioka, Wojciech Roga, and Mark Wilde. So the main goal in this work is to study GHZ distillation in 3 regimes, which is GHZ distillation from quantum states, from quantum networks, and from quantum networks with repeaters. Okay? So the question that we address is the following. We're given n copies of a multipartite state, rho A1 to AN. So this is a state that's distributed between n nodes. And then the question is, how many copies of GHZ states can you distill from these n copies of rho? And you're allowed to perform local operations in classical communication. So the GHZ state, the 3-qubit GHZ state is written in the first equation. Okay, so what we want to study is the rate of GHZ distillation, which is just given here, log 2 of m by n, where m is the number of copies that you distill and n is the number of states that are required to distill those copies. And then this is the state scenario, and then we move on and study this in case of quantum networks and then quantum repeaters. Okay, so in general, the rate of GHZ distillation, that's hard to characterize, and there have been some previous results as well. So capacities are hard to find, and therefore we look at the upper and lower bounds. In this work, we give the upper bound, which is called the recursive cut and merge bound, which I will get to in a while. And we also give lower bounds for certain multipartite states. These multipartite states, these are the product of pure bipartite states, which are just which is given by the Bakst equation. So if you have a state sigma A1, A2, A3, A4, and you can express this as products of bipartite states, that's what you call as product, that's the multipartite state under consideration. And so this is an example here of the state. There are 4 nodes, and they're sharing row A1, A2, A1, A3, and so on. You have n copies of these states and want to distill out some GHZ states. Okay. So we first find these bounds for the multipartite states, and then we convert these bounds to the channel scenario. Okay, so first let me define what is distillation of GHZ state from a multipartite state. So you're given m parties, and they share the state row. Then we call, we say that there's an nr epsilon GHZ distillation protocol, and it's defined as just an LOCC, which acts on n copies of rho, and it generates a state omega, which is close to a GHZ state, which is given in the first equation here. Then the key rate is given by this R, and we say that R is achievable if there exists such a protocol. And then the GHZ distillation capacity is just defined as the supremum of all these achievable rates. A simple way of thinking about this is just to think about, can we construct a protocol for rate R with epsilon going to 0 and large n? So it's just a, yeah, okay. So let's just consider one simple example. We're given this state where there are 3 parties, and each of them share a bipartite state, a Bell state, phi A1, A2 or A1, A3, and phi A2, A3. And they have 2 copies of this state. Okay? Then you can perform the following LOCC protocol. You take 2 Bell pairs, phi A1, A2 and phi A2, A3. Then A2 acts like a CNOT gate and then performs a measurement, gets an output, and communicates this to A1, A3. And then the state that is present with A1, A2, A3, that's a GHZ state, right? And then if you have 2 copies of this state, that implies you can produce 3 copies of GHZ state, which implies that the rate is equal to 1.5. Now the question is that, is this the best protocol that one can perform? Is this can you do something else which will give you a higher rate? And this has been an open question for for 10, 15 years, I think. And here we prove that that is the case. This is the optimal protocol. and we use the recursive cut and merge bound to prove this. Okay, so what I'll do now is just introduce the recursive cut and merge bound, and for that I need a few basics. The first one is the relative entropy, which is just given in this first equation. And then we can define, using this relative entropy between two states rho and sigma, we can define the relative entropy of entanglement of a state rho AB. So the way you define is, you just perform you have an infimum over all the separable states, and so this gives the relative entropy between A and B for the state rho. We can also define range relative entropy of rho AB. Here, the only change is that you replace the sigma AB, like the infimum over, instead of the separable state, you have the PPT states. And the range relative entropy is always less than the relative entropy of entanglement. So the reason we need these two quantities is that the relative entropy is relevant for key distillation, and the range relative entropy is relevant for state distillation. Okay, another concept that I need is that of non-trivial partitions. So let's say that you are given a set which consists of A1, A2 and A3. Then the non-trivial partitions are, you have A1 on one side, A2, A3 on the other one. You have A2 on one side, A1, A3, A3 and A1, A2, and in the fourth one you have all of them separated. So A1 is separate, A2 is separate, A3 is separate. So that is the non-trivial partitions of the set A1, A2 and A3. Okay, so with this we can define the recursive cut and merge bound. So we are given a state rho, A1 to AN, and you consider all non-trivial partitions of this set. So let's just first consider one particular partition, and let's call that P. Okay. Here GIs, these are just groupings of AIs, right? Okay, so now we can, what we do is we define the RCM bound for a particular partition P. So let's start with that. So there is just a constant term here which is dependent on the length of your partition. So the first term, what you do is you define the relative entropy between G1, which is like your first partition, and everything else. In the second term, what you do is you define a new state, which we call as rho tilde, and the way you define this new state is to partition partition the G1 between G2 and everything else. Okay, so the way you do this is you tensor in a ancilla system, you apply an isometry, and you split G1 in two parts, giving one to G2 and one to everything else. Now you can define a relative entropy between this G1, G2 and G1 prime and G1 prime, G3 and till Gp. And in this way you define, so first you define a new state with G1 split, and for that new state you define a relative entropy of entanglement. And there is a minimization over all the ways in which you can split G1. So that corresponds to a minimization over all the isometries. So that forms your second term, right? And now for the third term, what you're going to do is split G1 and G2 into parts between G3 and everything else, and you go on doing this till you reach this end term. So what you do is you have a state, you take a partition and you define the RCM bound for that particular partition. Then and you do this for all possible partitions of the set A1 to AN. And then the RCM bound for the state is defined as a minimization over all the partitions. So this is a very complicated measure, but it ends up being that for multipartite systems, the measures most of the measures end up having some complicated properties. Okay, so So this is the RCM bound for a multipartite state. So here what you can do is just replace the relative entropy of entanglement with the Lorentz relative entropy, and you can define this RRCM as well. And right. So let's just take an example. Let's say that you have a state rho A, B, C. And so these are the partitions which I talked about. So it's you have 4 non-trivial partitions. So the first, the RCM bound corresponding to the first partition, that's just the relative entropy between A and BC, right? And then you have the RCM bound for the second partition, which is again relative entropy between B and AC grouped together. Next you have the relative entropy for the third one, which is again, sorry, you have the RCM bound for the third partition, which just ends again being the relative entropy. And it gets a bit more interesting when you consider the fourth partition, which is A, B and C all separated out. So what you have here is a half, which was coming from that constant factor in front of the definition. The first part is just a relative entropy between A and BC, and in the second term, what we do is split A between 2. So that's what you see here. So you split A into A bar and A prime, and that's what you end up defining. So and then the RCM bound is just going to be a minimum over all these RCM bounds for the partition. And now if I calculate this RCM bound for the state that I considered before, in which you had a tensor product of Bell states. Okay, so sorry, I should get to that later. Yeah. Okay, so the next theorem that we prove is that this RCM bound, this upper bounds the distillable GHZ entanglement. And this is the definition of capacity that I gave before. Now, when I use this theorem in this case where I had products of Bell states, I find that the RCM bound calculates to 3 by 2. And in this way we end up proving that the protocol which I introduced before and so the protocol gives a lower bound, and the upper bound that I have here, they coincide. And in this way you prove that the capacity ends up being equal to 3 by 2 or 1.5. Okay. So to prove this, there were certain properties that we had to show. The first one was monotonicity under local operations and classical communication. And then we had subadditivity under tensor products. And then we had asymptotic continuity and normalization. So just by using these 4 properties, you could prove the upper bound on the capacity. Okay. Okay, so I talked about this particular types of multipartite states, which I called the product of bipartite states. So in general, the RCM bound, it can be very complicated to calculate because of the number of partitions that you have. However, for this product of bipartite states, we can see that the bound simplifies a lot. And this is the simplification that I write in this box. So let's look at this one. So you have 4 nodes, and this is the state that this is the state which is shared between these 4 nodes. And then what you can do is, let's consider one particular partition. So let's consider A1 and A2 on one side and A3 and A4 on the other side. Okay. Then this upper bound collapses to the following. So you have the constant factor, but the sum now runs over the states between row A1 and A3, A1 and A4, and A2 and A4. So okay. So yeah, so the sum just now runs over the states which are across the partition. So this simplifies quite a bit, and useful, as I will show later on. Okay, so this is the upper bound for the product of bipartite states. Now what about the lower bounds? What kind of protocols can we use to distill out GHZ states? So this is one protocol. So what you do is that you make each of these nodes perform an LOCC operation. So LOCC is again local operations and classical communication. And you ask them to distill out bell pairs. So each of them, they distill out some MI bell pairs. For example, this A1, A4 distills out M1 bell pairs and so forth. Now this, the number of bell pairs that can be distilled out from n copies of a state, that's actually lower bounded by the coherent information of the corresponding state. So they do this protocol, distilling out bell states, and then they perform the following. So this is the protocol that I introduced for the GHZ states. What they do is they take two bell pairs, perform a C0 gate and a measurement, and they keep on doing it with, they keep on, like the adjacent pairs keep on doing this protocol. And once they do this protocol, they get a GHZ state shared between these M parties. However, the problem is that, okay, so they have to be very careful about how they choose the bell pairs, which bell pairs they are utilizing in their protocol. And this problem of correctly choosing the bell pairs condenses down, this problem of correctly choosing the bell pairs is equivalent to this pre-packing lemma, which from studied in graph theory. And then once we used pre-packing lemma with this protocol, we obtain the following result. Okay, so I already talked about the upper bound, and now using that protocol that I introduced before, I can look at the lower bound here. And just by invoking the coherent information and the pre-packing lemma, I get this bound. And the only difference is that instead of the range relative entropy, what you have is the coherent information. In certain cases, we see that these two bounds coincide. That is, the coherent information is equal to the range relative entropy. And that is true for pure states. So for pure states, we actually find the exact GHZ state distillation capacity. So if you're given a multipartite state, which is a product of pure states, then we know exactly how many states, GHZ states you can distill in the asymptotic limit. Okay, so I think this is quite a nice result. And okay, so right. So we consider the GHZ state distillation from multipartite states, and now we consider quantum networks. So in a quantum network, you'll assume you have each node is connected by a quantum channel, and that might be like an optical fiber, right? Now there are certain channels which are called as teleportation simulable channels, which are defined as follows. So let's say that Alice and Bob, they're connected by a channel N. Alice inputs a state rho A, and Bob gets a state rho B. Now instead of a channel, I give them a entangled state, omega RB, and I say that using this rho A and omega RB, you can use some LOCC operation. And if they can do an LOCC operation, which gives them the the same state as would have been obtained by the channel N, and this is true for all inputs, all Alice's inputs, then we can say that this channel is teleportation simulable channel. And if all the channels in your network, they have this property, then we call the network as teleportation simulable. And these channels are, you can just, if you just have a pure loss channel or like a beam splitter, that's your teleportation simulable channel. Okay, so what this means is that a teleportation simulable channel that is equivalent to a product of bipartite states up to an LOCC. So you can simulate your network by LOCC and these states. So now we can use the bounds that we have before for the multi-part product of bipartite states. And since the teleportation simulable network is equivalent up to LOCC to these states, we can just reuse the results, and we get the following. What happens is that just the state is the state that you have here. That's the state which simulates your network. Okay. So now we can use this result to study the capacity of pure loss networks, and we find the exact capacity for such networks. So here eta jk, that's just the transmissivity of your optical fiber, and again you see the sum is over the pairs across the partitions. Right. Okay. Now we can consider quantum repeater networks. So let's say that you're given 5 nodes, and 4 of them, they want to share a GHZ state. The middle one, for example, it's just helping these 4 states, these 4 nodes to distill a GHZ state. Now, what happens is we can use the bounds that we have before exactly. The only change is the way you define the partition. And the way you do that is, you consider the partition of the nodes that want to share the GHZ state. So in this case, it's A1, A2, A3, and A4. And then you kind of, so first you define those partitions, and then you add A5 to each of these partitions, and in that way you define a new partition, new partitions. And so this will actually give us the upper bounds on GHZ distillation with help of quantum repeaters. So let's consider an example. Let's say that you have 4 nodes and they want to share a GHZ state, and at this point there is no quantum repeater present. Then we can just use the theorem that I introduced for teleportation simulable networks, and we find this bound here. So we know that's the fundamental limit for this network. Now let's say that we add a repeater in there. So there is a repeater right in the middle. And now I can use, so what I want to do is, I want to find lower bounds and upper bounds with this repeater and see how much it ends up being. So let's just consider the first protocol. So this R, you can think of it as 2 point-to-point channels, and the only change here is the transmissivity. The only change because of the repeater is in the transmissivity of these connecting channels. And then you can use the theorem that I had, and then you just find the lower bounds for this channel. And we can also use the upper bounds that are presented in the last theorem. And once you do that, you can plot these plot the bounds. So here the blue one, this is the GHZ state distillation without a repeater. And then there is this red one, which is the upper bound with the repeater. And we find that the lower bounds that we have, the lower bound for the repeater, that is this green line which just overlaps with the red line. So we basically find that the fundamental limit that you can obtain with the repeater setting. So there is a lot of improvement in the high loss regime here, but not so much in the low loss regime. So so this is the example we can consider. Okay, so I'll just like to conclude. So what we have done is to establish the fundamental limits of GHZ distillation in networks with and without repeaters. And for this, we have introduced a upper bound on the GHZ entanglement and distillable conference secret key, and we refer to this bound as the RCM bound. The main takeaway would be that we have the exact GHZ entanglement of a quantum network, which is connected by lossy bosonic channels. And these correspond to the physical quantum networks which have optical fibers connecting the nodes. Okay, so that's it. Thank you for listening to me, and let me know if you have any questions.
All right, thank you, Anit. We might have time for one quick question before moving on. So, if not,
So you skipped on this very quickly. So in general, finding the partitions of an arbitrary set is a really hard problem,
Yeah.
right? And calculating. So then you made an assumption you're only going to look at the bipartite,
Mm-hmm.
and so your limits depended on that assumption.
Well, okay, so if you have such a state, which is just product of bipartite states, then the bound collapses to what I showed you.
Ah, I see.
Then you can just prove it. But if you have a multipartite state, the partitions are hard to find, but you're doing upper bound, so you just consider
Oh,
some.
okay, so any partition you find, the upper bound still holds.
Yeah.
Okay.
To follow on to that, isn't it true that as the network gets larger, these quantities are going to be NP hard to compute?
I think so.
Yeah, that's what I thought. That's where I was getting.
That's what
Yeah,
you're
but
getting
these-
at,
The
yeah.
partitions, finding the
But we still
partitions
have
of the set.
expressions for them that in principle can be calculated
Yeah.
given enough time.
A lot of time.
Well, I mean, you can consider some partition and just see what the limits are, instead of finding the exact quantity.
I think one would kind of expect that these things would be hard to calculate, given that they're related to.
You're trying to simulate a distributed quantum computer classically, so probably it's hard to calculate.
No, but it's related to graph theoretic problems,
Yeah,
right,
okay.
which typically many quantities of interest are NP hard to calculate.
Okay. Hamiltonian cycle problem, for example,
Yeah.
which I learned from teaching in the class.
Oh.
all right, we'll let's thank our speaker again and move on to our last talk of the day from Arshad Danagosian here at LSU. He's going to tell us about using coherent population trapping in the nitrogen vacancy center to model the nuclear spin noise affecting a qubit. So, and just to reiterate, after this talk finishes at
Whichever one's
after
faster.
5,
Okay.
we're all going to kind of gather, walk over to the Chimes restaurant, which is their like bar food, bar kind of joint. Good, on the north side of campus. We're on the south side of campus, so what's that like? Are we going to walk over there? Like 15, 20-minute walk, something like that?
Some people do have cars parked outside.
So we could do like
There's
a
a bus
combo
loop if you don't
carpool
feel like
slash.
It's
walk.
about a 20-minute walk.
So maybe we'll
Yeah.
carpool over there. Is there parking up there?
I actually fit in.
We'll make that decision, but we will
Fit in-
congregate
fit
out
in where
there.
it needs
There's
to.
parking behind the Chimes, right?
There is a bus route that actually
Yeah,
goes
there's-
right in front of our building and stops you about 3 buildings from the Chimes.
I usually park in the lot across Chimes Street. There's a C lot. It's free for anybody to park after work.
Oh, okay.
It's
Good to learn that.
All right, so it sounds like we'll probably get like a little bit of a caravan going on. I reserved a compact car as a rental and was given a minivan, so anyone wants to ride. I've got about 6 extra seats or so. Yeah.
Ryan has a pickup truck. We just stow everybody back there. Right, Ryan?
Doesn't often recognize when you plug it in after you.
What was the head count for dinner?
7 or 8.
Oh, my car alone will fit 7 or 8. So we're good.
So it's hard to compute partitions. I wouldn't have thought that. We just thought it was
Yeah,
like
I remember this
combinations
from-
or something.
From years ago when I was I have a double degree in PhD in math and physics. I remember in some math course we talked about partitions and NP hard. And there's like all of these, there's something called Bell states, which are different Bell and different states that allow you to sort of tabulate them, but it's I don't think it's NP complete even. I think it's NP hard, so it's not even an NP complete.
Okay, so, well, without further ado, here's our shot of this talk.
All right, so first of
NP
all,
centers.
thank you for staying. I want to also thank Mark for inviting me. I don't think he's here.
He asked me, who should I invite, and I said you.
Thank you. So, well, I'm going to talk to you today about a multi-university research initiative that's going on, and, well, specifically about a sub-project of that, and that's done with collaboration of Dartmouth College. All right, so let me first give you the big picture of what's happening. Well, the main part of the problem is, of course, how to deal with, let's say we have a computational qubit. Now, that computational qubit, which is right here, does experience some noise, right, which is in almost every problem. So that will, of course, interfere with our ability to do computations with that qubit. Hence, one way to deal with this problem is to specify a spectator system. Now, that is also present in this system, which again I'm going to talk about. That spectator system has the ability to measure the statistical properties of the noise and then do something useful with that. So for example, in this situation, what we're going to do, or at least what we hope to do, is to feed that information back into some sort of a machine learning algorithm, and that will be connected to a pulse generator, which is right here. And hopefully that pulse generator will give us some sort of a pulse sequence that will decouple the computational qubit from the noise, hence achieving the goal of getting a well-functioning computational qubit decoupled from the noise. All right, so that's the motivation. And I'm going to be talking about, as I said, a sub-project of this. So it's going to be mostly about the environment noise and how to analyze it using the spectator system. So let me give you an introduction of what systems we're using. Of course, as I said, it's as the topic says, it's about the nitrogen vacancy center. So let me first tell you about that. So a nitrogen vacancy center is a point defect in diamond. So what that means is that if you take the diamond lattice, you replace two nearby carbon atoms, you put, instead of one, a nitrogen atom, and the other one you keep vacant. So what happens with that is when you do that, what happens is that some of the p shell electrons of the nearby carbon atoms, as well as the nitrogen atom, are going to accumulate in the vacancy, hence giving us some sort of an electronic structure for the nitrogen vacancy center. And that's what you see here. Well, that energy, of course, that electronic structure has to satisfy some properties. So for example, it needs to satisfy the symmetry properties, the wave function specifically, has to satisfy the symmetry properties, as well as has to be antisymmetric, and so on and so on. The energy levels, what is special about this is that the separation from the ground state to the excited state is about the wavelength of a red light, which is optical. And experiments also show this system to have a total spin of 1, which means that the number of electrons in the vacancy is even. The current analysis in literature, which is by no means the final thing, but what we currently know is that the number of electrons there is about 6. There's also the possibility of having 2 electrons. All right, so that's the electronic structure of the vacancy, and that's what's going to be our spectator system. We're going to spectate the noise or analyze the noise using this system. I'm going to show you how we're going to do that, but first let me tell you what our computational qubit is. So the computational qubit is the nuclear spin of the nitrogen 15 atom that's residing in the MV center. The environment that's going to affect our computational qubit is going to be a bunch of spins, the spins of carbon 13 atoms, and those in fact make about only 1% of the total carbon atoms in the diamond lattice. And that's because about 99% of them is carbon 12. They don't have ground, they don't have nuclear spin states in their, they don't have nuclear spin in their ground state, let me put it that way. All right.
What?
What?
They don't have nuclear spin
In their
period.
ground states. Yes, the S is equal to 0 in their ground state, the nuclear ground state. For carbon 12, for carbon 13, they have a spin S equals 1/2. So what's happening is that you're getting a dipole-dipole coupling between the carbon 13 nuclear spins, which are right here, and the nitrogen nuclear spin right there. So that's where the noise is coming from. All right, so I guess we can move forward. Let me now tell you how we engineer the spectator system. I told you it's going to be like this, but it's in fact more specific than that. All right, so here's that system again, the electronic structure. What we do is that we try to restrain the dynamics into a 3-level system. That's just one excited state and 2 ground states. This structure is usually called a lambda system. And we do that using 2 laser beams, a red laser and a green laser. Now, because the excited states are, well, there are a lot of excited states actually, there are in fact 6 of them. We have many peaks, we can do this in many different ways. The way we prefer to do it is, of course, the one by which this system will be the most close to a closed system. That is to say, you don't have any transitions happening outside this 3-level system, right? And the literature says that to have the best chance of getting no transitions outside the system, the best pick will be to pick the state that has the group theoretical notation A2. Those are just some group theoretical notation.
And Arshad, you went very fast, so maybe just one more time.
Sure.
What is the role of the spectator qubit versus the computational qubit? Not for me, for everybody else.
Good. So for the computational qubit, of course, the main point is to do computations. The spectator qubit will analyze the noise that's affecting the computational qubit. And the way it will do that is, first of all, it has to be close to the computational qubit so that it will register approximately the same noise, and it has to have some physical properties that allows it to measure the noise in some sense. So some phenomenon has to show the effects of the noise when being subject, well, let me try to rephrase that. So some phenomenon has to register the effects of the noise when that noise is affecting this spectator system.
And once we get the noise from the spectator,
We can do many things with it. So the one that
name one.
right. So we'll do dynamical decoupling, which means we'll try to apply pulse sequences based on the information we gathered, and those pulse sequences will allow us to decouple the computational qubit from the environment, meaning that we will not have decoherence, at least for a set period of time, which allows us to do computations from there. All right. So this will be our spectator system. It's not this, but it's a restricted dynamics of that. And we do that using 2 laser beams. All right, so now that we have our spectator system, what's gonna be the phenomenon that we're gonna use in order to register the noise? That phenomenon is gonna be the coherent population trapping. So let me tell you a little bit about that. So let's say we're trying to pass a green laser through a system, a 3-level system that has this structure. Now, what would you expect? So if you're trying to pass a green laser that has almost the same energy as the separation energy between the ground and the excited states, what's going to happen is that the green laser is going to be absorbed, going to be remitted in some other direction, so you will not have any transmission happening on the same direction where you applied the laser pulse. So, and that's what you see here. So, for example, this is done for strontium paper. The x-axis is the green laser detuning, and the y-axis is the transmission. So you see that there is no transmission where the detuning of the laser happens to be exactly equal to the energy separation. That's what absorption is, right? Well, if you apply a red laser now, something interesting will happen. Now, what you do with a red laser is that you apply it such that it will be tuned with the other transition frequency of the second ground state with the excited state. If you do that, what will happen is a destructive interference. Here's how to think about it. So a destructive interference will happen between the transition probability amplitude from the first ground state to the excited state, and that will destructively interfere with the other probability transition amplitude from the second ground state to the excited state. Due to that destructive interference, what will happen is that there will be no population in the excited state. Now, what will that lead to? That will lead to no absorption, because that will require us to excite an electron, say, from the ground to the excited state, right? So you will get no population in the excited state due to the destructive interference, and hence you will see some transmission of the green laser when this destructive interference is happening exactly, which is where the detuning is 0, right? Other way to say that is the green laser wavelength is exactly equal to this separation between the two energy levels. All right. Another way you could describe this is by this plot. So what you could say instead is that the excited state population reaches a minimum of 0 to be specific, when your green laser and the red laser are just exactly tuned to those energy separations in your system. And of course, this is called a coherent population trapping. It's called population trapping because your population is literally trapped in the Hilbert subspace of the two ground states. There is no population of the excited state happening here. This is also known as an electromagnetically induced transparency, by the way, for the experts. Yes?
So, are we trapped in rest states? Yeah, like combination of like this G1.
Good. So here the treatment of the electromagnetic field is that we're assuming it's classical, which means there will be no dress states, because the dress states will need both electron states and quantum, how to say it, and field states, right? But the thing is, I'm not treating the field quantum mechanically, so we will not have dress states. But instead, what we'll have is dark and bright states. If you're familiar with the literature, that's what we'll have. Yeah. All right, so this is the phenomenon that we're going to use to spectate the noise. Now, the question is, we first need a model for the noise before we spectate it, because having different models, we can come up with different results. So I want to first tell you what the model that we're going to pick is. But before I do that, let me tell you how noise is usually dealt with in quantum mechanics. So consider a qubit. You have your qubit right here is in a superposition state. The way you would treat the noise is by taking into account the environment surrounding that computational qubit. So in our case, that will be the carbon-13 atoms. So the carbon-13 atoms will have some state right here. And initially, let's say that they are separated. So the total wave function of the universe will be given by the tensor product of the state of the qubit and the state of the environment, right? Now, if you give this system some time, the wave function will evolve, and what you'll get is an entanglement between the state of the qubit and the state of the environment, right? So that's what we have right here. And if you want to now describe what's happening to the computational qubit, you will no longer be able to do so using a wave function. You can only do that using a density matrix. So the effective evolution will turn out to be such that there is some sort of a noise driving the evolution. So what that means is that the Liouville equation will have an extra term there, and that term will be a dissipative term. You've seen that earlier in the talk as well, with some other talks. All right, so what this is gonna mean for our system in specific is that our computational qubit is going to become, in some sense, classical. The reason for that is because this final state is a classical mixture between a 0 and a 1. There's no superposition in here anymore. So this is what a noise will entail if applied to a computational qubit. And ultimately, we want to avoid this. So there's a similar way to describe a noise, but instead of doing it quantum mechanically, that is to say, treat the environment quantum mechanically, you treat it classically. And that's what we do in our research. So the way we treat it is that we consider the carbon-13 nuclei. By the way, this is affecting now the lambda system. In the last slide, I was showing the qubit, but here it's a different system, but the principle is the same. So you have the spin bath, which is modeled as producing a fluctuating magnetic field, and that fluctuating magnetic field is the one that's affecting our computational qubit, or in this case, our lambda system, right? So, and that fluctuating magnetic field will be added to the external one, that we are already applying. Of course, that fluctuating field will also have some statistical properties. For example, the average of that field will be 0, and it will have some two-time correlation function, which we don't necessarily need to specify, but I will do it because that will help us find out the best decoupling pulse sequences at the very end. So I can go a little bit deeper into this and tell you what the noise model is. So if you consider a two-dimensional picture of what's happening, this is the diamond lattice. I think maybe I should fix this.
I'm enjoying the disco light show.
All right, this should do. Okay, good. So this is our
carbon-13 atoms just messing everything up.
Yeah. So most of them are carbon-12. Those are the carbon-13 atoms, and they're dispersed in the lattice. That's because they're about 1% in their natural abundance. So those are the nuclear spins that are affecting the qubit here, but not only the qubit, also the spectator system. Both of them are sitting in the nitrogen vacancy center. So in detail, what that means is that if you pick the ground state, one of the ground states of the electronic structure, that will have various separations, and those are due to the hyperfine splitting. So the closer the carbon-13 atom is, the more, or rather the larger, the hyperfine separation. And what we'll have here is that as many separations as there are carbon-13 nuclei. That means that we can describe the total magnetic field as a sum of individual magnetic fields produced from individual carbon-13 atoms, or nuclei, I should be careful. All right, and each one of them has some value. That value depends on how far it is from the MV center, and there is this stochastic process, which is a Poisson process, that will describe random flippings of the nuclear spins that are causing this fluctuating magnetic field to happen. So if you want to know what the expectation value is for the number of flippings per second, what you'll need is a noise parameter, and that noise parameter enters into the formula as follows. It's just the it tells you what the expectation is to have it tells you what the number of flippings, expected flippings is per spin for a certain period of time t, right? Because this is the Poisson process. All right. So that's that. Now this is the noise model. So what are we going to do with this? As I said, what we're going to do is to try to map this noise parameter into the coherent population trapping picture that we'll get, so that we will be able to tell what's the value for the noises just by reading the coherent population trapping plot at the end. So here's the results. First of all, this is done by an experimentalist group. They're our collaborators from the University of Oregon. What they measured is the fluorescence as a function of the detuning. The fluorescence is proportional to the excited state population, so it's practically what I've been saying before. So as you can see, there's a dip in the excited state population as the detuning is just right. Now that dip doesn't go to 0, and that's the important marker here. That height from 0 will in fact be able to tell us what the noise parameter is in our model. To check that, we in fact did a simulation, taking the noise model to be as I said before, and we tried to simulate basically the steady state solution of the dynamical equations using the noise model. And what we got is also a similar result where the excited state population, it goes to its minimum value. So there is some sort of a destructive interference, but that destructive interference is not exact so that it will go all the way to 0. It goes to some value which is close to 0, but not exactly 0. And that's the marker of the noise on our spectator system. So what we claim is that that height from 0 will tell us what the value for the noise parameter is. I can show you that on the next slide. So right here, for example, the blue line will tell you what the, will show you rather what the what the CPT plot would have looked like in case we did not have any noise present. But since we have noise present, what you'll get is something that doesn't go all the way to 0. So it ends up right here. And that height will be in one-to-one correspondence to the value of the noise parameter. Yes?
So I was curious, so like, did you simulate this BI by like sampling from Poisson distribution?
Well, that's a good question. In fact, I only needed to know what the correlation function is for my simulation.
I see.
I didn't need to simulate it. I didn't need to simulate every individual BI.
Yeah, just like a kernel.
Just the correlation function told me what the dynamics should look like, and that's very important.
Yeah.
What matters in the dynamics is just the correlation function, not any other higher order cumulants. Right. All right. So yes. So what I was saying is that this height is in one-to-one correspondence with the value of the noise parameter, which means if we were given this plot from experiment and we can know this height from that plot, then we can relate that to a specific value of the noise parameter, meaning that we'll have a complete model of what the noise looks like acting on the MV center. Now, with the time that I have, let me tell you how useful that information will be. So for the experts, I apologize. I'm gonna break this down. I'm gonna break down the dynamical decoupling into maybe too simplified of a scenario, but that's fine. All right, so here's what we're gonna do with that information. Let's say this is our computational qubit, and this is the off-diagonal element of that qubit. So it's not 0, which means that there's some kind of a superposition. It could be 1/2, for example. What would happen if you have the environment is that you will have the qubit entangled with the environment. So if you look at the density matrix element, it will go down. The off-diagonal element, that is. It will go down, meaning that the superposition will start to vanish. However, what you could do, given the information of the noise parameter, you could know when to apply a pulse. So right here, for example. When you apply the pulse, the dynamics of the off-diagonal element will start to reverse, and it will start going back to its initial value. So, and that's what you'll see here, and that's and in this very instant, what will happen is that there will be a disentanglement. It's instantaneous, but there's still going to be a disentanglement between the environment and the computational qubit. Now, specifically for this case, it's going to be disentangled, but with a phase shift. It's minus its initial value, so what we'll have to do is to apply yet another pulse. It's pi pulse to be exact. And that pi pulse will bring this off-diagonal element back to its initial value. And that will complete a dynamical decoupling sequence where we'll be able to get the initial value for the coherence of our computational qubit after a set period of time. Now, to do this in a more complicated scenarios requires us to know the statistical properties of the noise, and that's what we're doing here by finding out the noise model in our noise parameter. That's what we're gonna able to do in the future, hopefully. All right, so I guess I can give you the conclusion of what I've been doing so far. So the problem at hand was to take a look at the computational qubit and try to see how we can maintain its state for the longest possible time. So that was the set problem. The way we dealt with that is that we first of all had to isolate a spectator system. That system will analyze the noise that's affecting the qubit, and it will hopefully tell us what the statistical properties of that noise is. So we do that using the coherent population trapping phenomenon. That's how we record the noise, and we obtain a one-to-one correspondence between the minimum of the coherent population trapping, well, let me put it this way, the minimum between the fluorescence at the detuning delta equals 0 and the noise parameter value for our model. And for the future goals, what we want to do with this is that we want to write down a machine learning algorithm that will be able to produce dynamical decoupling pulse sequences to decouple the qubit from the environment. And hopefully we'll be able to do this in real time, but that's a long shot, and we'll try to see what happens. All right, so acknowledgements, that goes without saying, my friends from LSU. Of course, we were collaborating with Dartmouth College, so I want to thank them as well, my advisor, the experimental group from the University of Oregon, and the funding agencies. The paper will hopefully be submitted soon, so we'll see. All right, thank you very much for listening.
Alright, thank you. And does anyone have any questions? We're a little past 5. We can take an extra minute or two if anyone has any questions for Shag. Yes.
When you decide the Lambda system, like I think you mentioned Misha Lukin and somebody else at the bottom, but I couldn't tell whether that was a reference or just their like affiliations.
I'm sorry, yeah. They are references.
Okay, I just couldn't read.
Oh, yeah, they are references, yes. I'm sorry.
So does Misha Lukin do ND centers? Is that
He does
his thing?
many things.
Okay.
But he does NBs, he's got a,
Amongst other things.
he's got a spin-off company to use them for quantum magnetometry. So instead of a qubit for computation, it's very sensitive to small magnetic fields.
Any other questions for, yeah?
So you take this B parameters with, or like B tau parameters with N, right?
Yes,
But yeah, for the simulation you said like you are using some correlation matrix?
the correlation function, yes.
Correlation function.
Two-time correlation function, to be exact. Yeah. So the tau parameter there appears in the two-time correlation function. The two-time correlation will basically be an exponential decay, where the decay is described by that tau parameter.
So you add this stochastic terms like Monte Carlo?
No, I don't have to do that because those dynamical equations are just differential equations. You can solve them without using the Monte Carlo. Yeah. As long as you know the correlation function, of course.
All right. Well, if there's no other questions, I guess we'll just thank Arshad again. And let's sort of congregate up there, kind of see who's going to dinner, who's not, and figure out some transportation.
Thanks to all the speakers for making for a very nice quilt day, and we'll be in touch about the next.
Very good. The reason I stopped in the middle is you went really fast through the first slide and dived into the spectator.
Right.
And even I have trouble understanding what the role of the spectator and the computational. So I thought if I didn't follow that jump, maybe other people.
Yeah, that's understandable. So I was trying to make up for the time.
Right.
Yeah, and thank you for that. You were keeping a pretty good schedule. So it's a nice talk. Well, so if you're just trying to figure out the effect of the lines, the nitrogen spin, why don't you just measure the nitrogen spin? Why do you measure the spectator?
The thing is, yes, good question. The thing is, we don't want to measure the nitrogen spin because we want to maintain its state. If it were in a superposition state, one of the computations with that superposition state, we don't want to destroy it.
Yeah, that's the whole, this is a $6 million grant from the Army, and to study two qubits which are not even coupled to each other. Okay, so it took me a long time to figure that out. Okay, so the idea is you measure the noise, and the problem is they do this already, but they measure the noise globally throughout the dynamo. But that doesn't tell you what the noise is going to be locally because that depends on the carbon 12.
Right, and that's why you have these spectators as an exactly the same application. Yeah.
Just think about the
Well,
that's why I was
project.
surprised.
It's not just this problem. It's
Yeah.
many problems.
We also have a superconducting version, an ion trap version, but it said you must have a spectator qubit, a computational qubit, and it must use machine learning. That was it. Must use machine learning. And I go, all right, machine learning it is.
My other question, and I guess you actually answered this now because that's what the grant is asking. What if you just, so do these NV things, are they manufactured, these diamond things, or are you just mine some diamonds in South Africa and buy some for
You do manufacture them.
and why not just filter out all those bad isotopes?
Oh, let's do that.
Right, and that's exactly what they've been doing.
But they've been trying, okay, so here's the point. Okay, so if I buy, what they take is regular diamond, mercury diamond, and they implant the NB centers using ion implantation, okay? So if I want to buy, base my thumbnail, and if I want to buy one with just the regular carbon 12 regular diamond, it's 10K. If I have them make me one with, and that's 1%, right?
Yes.
If I had to make me a chip with 0.1%, that's 100K. And if 0.01%, that's $1 million.
I think I'm
Filtering out these eyes.
Right, it's very, very